First of all, good morning. Welcome to the IT Center. Welcome to PPCES. So, in terms of overview, we are at the last day. So the couple of days before were allocated for MPI, which is the message passing interface, and OpenMP. So basically parallelization across compute nodes and within compute nodes to basically utilize the full capability of the systems. This day will have a slightly different focus: machine learning, AI, and deep learning. Okay, and before I go into detail, I first have to do a little bit expectation management. So we try to make that very clear on our website. We have one day. This will not be a very high in-depth course. So basically, what can I expect from this workshop? We will not cover in-depth mathematical background. I will give you a slide overview about how machine learning and deep learning works, also with a slightly in-depth view on deep learning, but we will not deep dive into the different topics. We don't have time to discuss every last feature of every framework. So I have collected some further links that are also attached to our PPCES website, but we will not have time to discuss that today. So typically you need a couple of days workshop in order to do that. And unfortunately, we will also not have time to cover advanced topics such as large language models, reinforcement learning, which are very interesting, but at a certain point we need to do a cutoff, and this is basically an introductory course to machine and deep learning. So on the contrary, what can you expect? So as I said, a general introduction into machine and deep learning. We will look at different scenarios such as supervised and unsupervised. I will explain a little bit about that, what that means. We will look at different techniques that could also be useful for your workloads or your research, such as classification, regression, clustering, and also preprocessing, which is often underestimated. A very important question that will pop up is what is the best technique for my use case? I will shortly go in that direction and try to answer that. There are also some useful links that are attached to the slides where you can find more information and basically find help to select what is appropriate for you. Then additionally to machine and deep learning, we will look at the operational side. So we have a large HPC cluster here, and the question is, how can we execute such workloads on our cluster? Because if you know the basics and the theory, that's good, but if you cannot execute that, that's bad. So we will also cover that, because this is also what we are here for. So we will have a look at available hardware here on site, as well as software for machine and deep learning. How to run that. We will look at containerization. We'll look at two packages in detail for hands-on exercises, which are scikit-learn and PyTorch. And I will also show you a bit how to identify whether your workload is consuming enough resources or not. So basically look at the GPU side, whether you basically utilize it correctly. Good, and then at the end we also have some, or in between and at the end we also have some hands-on exercises. And so basically the agenda for today is split. So first we will look at a general introduction to AI, machine learning, deep learning. Then we at 10:30 we have a short coffee break for half an hour, and then we go into part 2, which covers execution options for machine and deep learning. And the first lab. After the lunch break, we will then look at deep learning, how deep learning functions, and also how to distribute it across multiple GPUs, but also potentially multiple compute nodes with multiple GPUs. And then we have another short coffee break, and in the end we have some time for labs, especially in the context of PyTorch. So as you already see, I did not prepare the slides alone. So we have some contributors here that I listed. So one is Georg Zitzelsberger. He presented a similar workshop in last year's, and we took some of his content and integrated it into our slides. And I have some colleagues here from the IT Center, Dominik and Radita, who contributed. Good, so all the slides for all the different parts are on the website already, so you can download, you can have a look at that. Labs are already online, yeah. So, but we will go through that step by step. If you have any questions in between, just raise your hand and we will directly address that. Good. So that's the agenda. What kind of hardware are we using today? So basically, we use our ML segment, so which stands for machine learning, from our current up-to-date CLEX 2023 cluster. Yeah, so it was installed in 2023, start of 2024. So it's pretty recent and comprises big compute nodes. So you see a sketch here on the right-hand side. So we basically have 2 CPUs in each node and 4 GPUs in that system. And these GPUs are not regular consumer GPUs, but basically data center GPUs, NVIDIA H100, the current Hopper technology. There's also H200, but this is pretty recent. So large memory GPUs, and they basically provide a lot of compute power for machine and deep learning workloads. All these compute nodes are also interconnected. So we have here a high-speed HPC network, which is not really comparable to a network that you have at home, like Ethernet. You probably have 10 gigabytes per second at home. If you're lucky, sometimes only 2.5 or 1 gigabit. Here we have 200. Yeah? So if you need to exchange data between the different compute nodes, this is pretty fast here. Okay, and then what I already teasered, we are involved in 2 different initiatives as well. So one is called EDI Rheinland, which is a consortium of different partners. And they basically provide different services. Here at the IT Center, we are, for example, involved in consulting services for parallelization, such as MPI, OpenMP. So basically help you to get your codes faster. Different other partners have different other services or provide different other services, but this is basically our share in EDI Rheinland. And the second one is West AI, and so we are basically part of one of 4 AI service centers in Germany. And in that context, we provide different services like consulting in the context of AI, hardware as well as hardware resources, so basically access to H100 GPUs, and also trainings and tutorials. So if your institute or your company requires any support or any consulting or hardware resources, please get in contact with us and we can discuss and help you. Good. So first is introduction to AI, machine and deep learning and preprocessing techniques. So basically, I've been at a conference a couple years ago. So it was a large conference in the HPC sector. And someone who studied that, such as me, so basically I did my master's in AI and machine learning. I was pretty pissed because basically people were putting all those terms, AI, machine, deep learning, and they were using these terms interchangeably. And these are not. Yeah? So basically we do some categorization first. So artificial intelligence is basically, as you see it here on the left-hand side, our main area. Yeah? It's a very broad area, and it does not just cover stuff like machine and deep learning. Yeah? So there are different other aspects like learning, like reasoning, problem solving, understanding stuff. There are different other aspects such as game theory. You heard of chess computers. smart algorithms, that are not part of machine and deep learning. So it's a very, very broad topic, and this is not just purely relying on data, but you have different disciplines where these might be used. So like computer science, psychology, chemistry, linguistics, and so on. In principle, we distinguish, so we categorize those AI capabilities in different categories. So one is narrow AI, and I basically looked that up. So there are different definitions of it, but basically one definition says narrow AI is designed to perform a specific special task and is only designed for that, such as image recognition or text recognition. And then we have different places in between, and what we are currently reaching with pretty recent advances such as large language models and multimodal approaches is general AI. And basically the idea here is basically you have an AI that can perform any task such as a human. So there's also one term ahead of that, so basically one step better, which is called super AI, and this is basically the idea that this AI can surpass a human in any task. Good. Machine learning is just a subset, as you see it on the left-hand side. So it's not basically covering everything that is in AI, but it's a subset. And the idea here is basically we can learn from data. So we have some kind of data set. Often that is structured. So structured is it has a fixed structure. You can always rely on that. And basically the idea is what can we get from this data set and what can we learn from that? So it's a very, very specific subset. Typically what we use here is numerical and categorical data. So for example, prices or categorical data where you have some fixed labels, some fixed amount of labels that you want to predict, for example. And then we have deep learning, which is again a subset of machine learning, and not just a subset, but also a specialization, because it can not just handle structured data, but also unstructured data, such as images, text, where you cannot really see a structure yet, but deep learning can figure out a structure or figure out information from the different data sources. So these are much more sophisticated algorithms, and typically the term that you heard often is deep neural networks, and we will have a look at that today. And a couple of years ago, that topic was not very well embedded in the different research areas yet, and people were using these terms interchangeably, although they were meaning different things. And this is just a very brief categorization. Good, so I will first start with machine learning before we dive into deep learning after the lunch. So machine learning, we have different disciplines. And here we have different scenarios. First, we will start with supervised learning. And supervised learning, typically your data set consists of features. So basically you have features that describe your data entity or data sample. And then you have labels, and labels is basically our ground truth that we want to predict or that we want to use as truths for different algorithms. So label is basically you have already your target variable and you have instances where you already know what it should be, what is the result. So here we basically have two different techniques. One is classification, and here the idea is basically to categorize objects and assign them to one or more classes. We see that here on the right-hand side. Give me a second. Laser pointer is a bit better. We see that here on the right-hand side. So we have different data samples that are either red or blue, and we want to create a model that is able to predict the class of unseen objects and assign them to one of those classes. So this is basically classifications. There are different subsets of classification. One is 0-1, basically binary classification. And what you see here, it's either this or that, but not both. and then there's also multi-class classification where you just don't have one or the other, but basically 10 or 20 or a defined number of classes. The other one is regression, and there we basically do not deal with categorical data, but our target variable is a continuous value. We see that here also on the right-hand side, we have some data elements and ground truth labels, so these are the dots, and we want to create a model that is basically able to predict unseen data samples and assign these continuous values and predict those. Good. Then, contrary to that, we have unsupervised learning. And the biggest difference here is that we don't have a label. So we don't know the ground truth. We have some data that is describing our data samples, but we don't have a label at all. And the goal here is multifold, but mainly the goal is to find a structure in the data. For example, similarity of objects and group them together into clusters. We see that here on the right-hand side. There are different data samples, and you directly see from looking at the data that there are 3 clusters, but basically you don't have the labels yet. And the idea is to find those. But there are also different other techniques that are contained in unsupervised learning, such as dimensionality reduction. For example, consider a data set where you have 100 or 200 features per sample. So printing that in such a 2D representation is pretty hard, because you have 200 dimensions, and potentially some of the algorithms have really trouble with dealing with these 200 dimensions. And the idea of dimensionality reduction is basically to create a new data set that does not consist of 200 dimensions, but maybe of 10 dimensions, without losing too much information. So basically the distance or difference between those different samples should be similar. However, you want to reduce the dimensions. And there are 2 very popular examples, which is PCA, Principal Component Analysis, and autoencoders that are able to perform their task. Good, so these are the main disciplines, I would say. There are, of course, more. Semi-supervised learning, which is basically a combination of both. Sometimes you are dealing with structured data that does not have a label. And you first want to do some unsupervised technique to create labels and then combine it with a classification algorithm or regression algorithm, stuff like that. So there are combinations of both. And pretty interesting topic from my point of view is reinforcement learning, which basically does not use this ground truth, this label, but basically tries to develop a strategy by looking at feedback from the environment. So basically you select a certain action and then have a kind of evaluation mechanism from the environment where it's supposed to be that gives you some kind of reward. And if the reward is positive, it's a good choice. If it's negative, you need to tweak the features or the model a little bit. Pretty interesting example, Super Mario. So people used those techniques and said, okay, we train an AI that is capable of playing Super Mario. So they put it on a Super Mario level and it played for 100,000 of tries. And basically the reward was, if you do something good, great, that's a good choice. If you die, that's a bad choice. So basically getting the reward from the environment to train the model. And basically they created AIs that can do perfect runs in Super Mario. This is just one example. There are different others as well. So what is the typical workflow for machine and deep learning? So basically it consists of different steps. We have some raw data, we have a pre-processing phase, then we select a model and train the model. Of course, we need to somehow know, is the model good or bad? And finally, we want to use it in production. So basically apply it to unseen data. And we will look into all of these sections shortly, and I will explain a little bit about that. So raw data, and basically that's the same for deep learning. So or pretty similar. So basically we can also apply that to deep learning. So raw data, yeah. So basically, as I said, typically machine learning uses structured data, and this typically comes in form of matrices. So you have different features and a label, and you have different data samples. So it's typically a 2D matrix. But there could also be other kinds of data, like time series data. You have, I don't know, stock prices, stuff like that. Some monitoring data. You could have images, you could have text, you could have videos, different kinds of data. The question is just, what can I extract from those data samples and how do I present it to the model? And this basically comes in a second step, yeah. So, and this is often underestimated. So there's a lot of effort that you need to do here to have a clean data set that your models are also working fine and produce the desired result. So what does that mean? Cleaning, plausibility checks. If you have data that contains invalid data, missing data, you somehow have to eliminate those or replace that with reasonable numbers. Feature engineering is pretty important for machine learning. Although you might have unstructured data here on the left-hand side, you could extract or define features that describe that data and present that to a model in a structured fashion. Conversion, so for example, do you have categorical or continuous data, or do you want to, sometimes your data has different scales. For example, one feature has data that is ranging from -1 to 1, and the other one is ranging from -1,000 to +1 million. So if you present that to a model, it might be that the model will, favorite one of the features because of the scales. So data conversion and standardization, normalization of data is quite typical for pre-processing data. And as I said before, dimensionality reduction. So if you have high dimensional data, you probably want to reduce the dimensions to make it easier and faster for models to train. Good, then after that is done, so typically that's really underestimated and it's very important for the model accuracy after all. Then you need to select a proper model. So there are different model types, tree-based models, I don't know, so a lot of models and model types. Probably I will have a slide on that later. But it's not just the model, it's also the optimizer. There are different loss functions that are used for training. And all these different types have hyperparameters. You can have different knobs that you can tweak. It's not always the easiest thing, but typically frameworks that you will use have some reasonable defaults already. And then when you train or trained the model, the question is, how well does it work? So of course you need to figure out whether your settings, your hyperparameters, your data is producing a good result. So there are different metrics for that. For classification, you typically have stuff like accuracy, precision, F1 score, which is kind of combining those two and presenting an overall number. For regression, you have different ones because there is not a perfect match, but typically you are kind of close. So you have stuff like mean squared error, R2 error, mean absolute error, different metrics that you can choose that basically tell you whether your model is good or not. There are also techniques such as multi-fold cross-validation, very, very good approaches in my point of view, because it might be that you train your model, for example, for a classification task, with a lot of, let's say we have a 0 or 1 classification, binary classification. Sample is good or sample is bad. So if you train your model with samples and you have a 50-50 share of both, that's good, because your model basically knows what is good, what is bad, and there's a similar weight on those. But if you, for example, train your model with 98% of good samples and 2% of bad samples, it might be that your training is kind of biased to good samples. So if it predicts good samples, you're 98% of the time right. Yeah? So if you put in unseen data, it might be that it tends to say it's always good. Yeah? And multi-fold cross-validation is basically, so there are two parts of that. Yeah? So one is you split your data into different folds and then train different models and then basically average the results of those classifications. And then there's an extension for multi-cross validation, which is stratified. Yeah? And basically it tries to preserve the different proportions of good and bad in each of those folds. Good. So basically that's the general workflow. And typically what is done is now, if you're not satisfied with that, you start again to, manipulate or improve your data preprocessing, select maybe some different hyperparameters as soon as you are done and satisfied with the result. And after that, you can basically go into production, and this is basically apply that model in a productional fashion to unseen data. That's the general workflow. Good. Okay, let's look at some example with classical machine learning. Yeah. So for example, here we have unstructured data. We have images. They have a certain dimension. And basically the goal is to predict or train a classifier that can predict those images and assign them to a certain person. For example, here we see this is Mark. So in classical machine learning, what you need to do is use those images and then do feature extraction. So basically you define your features like roundness of face, distance between eyes. So basically you have the full power to define those features, and what you end up is a vector of features that describe your image. And your label is Mark. So basically classical machine learning, then you have different algorithms or classifiers available, support vector machines, random forest, which is basically tree-based, naive Bayes, decision trees, also tree-based, logistic regression, and so on. Ensemble methods is basically a combination of multiple models in one. For example, random forest is also kind of an ensemble method. And so basically you have different selections of the classifier, and the idea is you have features engineered manually or semi-automatically, and a label Mark, and train that classifier. So you train the selected model with many images with different labels, and step 2 is then apply that model to unseen data. And what's pretty important is any pre-processing that you do to these images also need to be applied to the unseen images. Otherwise, you have different data sets and compare apples to oranges. So if you have unseen data, you need to apply the same stuff that you did for the training step, and then you can basically put that in the classifier for inference, and it will predict what label it is. Scikit-learn, so this is a very famous library, so it's one of the most used libraries for classical machine learning and data preprocessing. So there are different utilities. We will have a look at those in a second. We have different machine learning methods. We have methods for visualization, so it's basically a Python library that also supports contains plotting mechanism visualization using matplotlib. So as I said, built in or built on NumPy side by matplotlib. Very, very famous, very broad, but focus is here classical machine learning. There are some multi-layer perceptrons that go more in the direction of deep learning, but typically this is a library that is executed on the CPU and not on GPUs. So it's open source. There's a huge documentation with examples. I linked that here. So basically we have building blocks that you can put together. As I said, there are different examples for different purposes. This is not very up to date here anymore. So the current version is basically 1.61 or something. So the slide is a little bit older here. Yeah, and basically you can install that in different fashions. So if you're on a local machine, it works also on the cluster. You can basically install that with pip or conda, scikit-learn, and yeah, then you get the full package and basically can directly use it in your Python code. Importing the packages. Here, for example, we used a support vector machine classifier with a certain hyperparameter set. So it's pretty easy to use. Good, so as I said, it offers a large set of services. We have methods and models for classification, regression, clustering, also some multi-layer perceptrons, but also it provides a complete utility set for data preprocessing, dimensionality reduction, model selection. It also has some predefined toy data sets. Yeah, so it's really, really powerful and really, really useful. Good, so here is just an image of the user guide. Yeah, so you basically also get guided through this different examples. You have supervised learning, unsupervised learning, model selection, and so on and so on. Yeah, so actually I really like that, and we use that in multiple bachelor and master thesis projects as well. Good, so here is a short example. So I said there are some toy data sets that you can directly use that will also be referenced in the examples online. This is an iris data set for classification. We have data sets for regression. Yeah, different kind of data sets from different disciplines. Different size of data sets. The digits is quite small. The diabetes and I think wine is a little bit larger. So basically there are some toy data sets available. Yeah, so typically you have X and Y. Yeah? So X is the feature matrix. As I said, we typically work with matrices, tables. So you have X, which are the features, and Y, which are the labels or targets in scikit-learn terminology. You also have information if it's a classification data set of how many classes there should be or there are. Okay, and you have some flags that you can set. For example, I want X and Y separate, or I want them packed together in one matrix. I can also say I want to have it as a data frame if I enjoy working with data frames. Yeah, so are different features. So here's a very simple example in a Jupyter notebook using the digits data set. So basically you have these images from 0 to 9, and you want to predict whether it's a 0 or 1 or 2 or 9. So yeah, this is just the loading the data set and printing one of those. So you have some documentation about the different data sets as I showed before. Good, but we will have basically a hands-on exercises where we can do clustering and classification as well. So I will not deep dive into that. Okay, so data preprocessing. I said that it's highly underestimated and often, especially in classical machine learning, it's really a pain to get the data set right. So typically the most important parts are missing values and feature engineering. So replacing missing values with reasonable defaults or removing, so cleaning the data set. Transformation and scaling is quite important. Yeah. So for example, standardization using mean and standard deviation to basically get them to a similar kind of scale, that the machine learning algorithm is not favoring one feature over the other based on the scales. There are also nonlinear transformations available and custom transformations possible. For example, if you want to do some custom stuff, you can basically build that in your workflow and integrate it. Good. Yeah, I don't know whether it's super important, but sometimes you want to do a little bit more data analysis with that. So discretization, binarization, and bins. So for example, pack everything that is between 0 and 100 into one category, everything between 100 and 200 into another category. So there are also features for that you don't have to basically implement that by hand all the time. So it's also utilized to reduce boilerplate code in your Python scripts. Here we see a small example. So we have a feature array X with different features. We don't really have a meaning behind the features. It's typically 2D. And we can pretty easily define the transformations such as standard scaling. So we basically say we have a standard scalar and we want to fit it to X. So basically it uses all those feature values or feature arrays to fit a scalar, and we can also print mean and standard deviation and scaling factors, and then we can transform our X to a scaled X. And basically if we have this scalar, we can also apply that to unseen data. So if we have another feature array that is unseen, we can basically just say transform unseen data because the scalar has been fitted to a certain set of training images. Is that clear? Or any questions? No questions? Okay. So that's what I meant. So basically it provides you stuff that you can fit and then apply to unseen data as well. So it's scalar, there are different other transformations where you can do that. Okay, so then feature selection. Sometimes, as I said, you have 200 or 2000 features, and the question is, which are the good ones? If you put everything in one classifier, it might be that it gets confused because it does not see the features that are really relevant for your classification or regression. And sometimes you also want to reduce the features. So option one is, how do you deal with it? Here, I basically want to have a subset of features that is best for my use case. So basically, if I have 2000 features, throw away 1900 and keep the 100 that are most relevant for my purpose, such as classification. And there are different techniques such as select k-best or select percentile, depending on what you prefer. So small example here, I have the digits data set, and I have X and Y. I want to have it both, so separate in two different things. And here I see this is linearized. So these are the different pixels in the image. So we have 64 in total, and we have 1,797 samples. So we have those number of images, and each image has 64 digits, so pixels. So here it's probably a nonsense example, but you could have different other matrices here. And here we want to select k-best, so has some certain hyperparameters, and we want to fit transform. So this is basically doing the stuff in one shot. So fitting the select k-best based on X and Y, because you need the labels as well in order to say, okay, what are the best features out of those? And then basically we get, so we here say K8, so we only want 8 features left after all. And then the new shape is basically number of samples, and we only have 8 dimensions left. And these are basically the 8 dimensions with the most information gain to basically solve this classification task. Pretty simple. So maybe an image example is not the best here, but you might have different data sets where you have different features describing an image, and then you basically can select the best features that can be used for your problem solving. Good. Option 2 is a little bit different. So how do I deal with large feature spaces? I can create a new feature space, which consists of a reduced number of features. So, however, I still want to preserve as much information as possible, and this is sometimes a little bit tricky to understand what is information. Information typically is the relative distance between the different samples. And if you have a high dimensional feature space, you have distance to the samples in each feature space. And basically, the goal here is to reduce the feature space, but keep the relative distance between the samples similar. There are different techniques, such as principal component analysis. And basically, the idea is I have here two components. I was starting with a 3-dimensional space, and I want to go to a 2-dimensional space. And I basically use single value decomposition techniques to define two components. And then the two remaining components is a linear combination of the other dimensions. So basically 3 dimensions will go to 2 dimensions, and these 2 dimensions, or the values of the 2 dimensions, are linear combinations of the full dimensional space. So there is one note that I put here on the slide. If you work with those, it might be hard to interpret these values. So if you look at that and you have, I don't know, a height of a person. This person is 1.8 meters high, this one is 1.6 meters high, and you have, I don't know, color of the eyes, or I don't know, age. Let's stick with some continuous values like age, height, whatever, some other feature that describes a person, and you want to go to a 2-dimensional space. These are linear combinations of those values, and you have values that you cannot really interpret or assign to a certain feature anymore directly by looking at that. So it's kind of tricky. There are options to basically reverse that transformation, so basically to go back from the 2-dimensional space to the 3-dimensional space. But this is just a note of caution that if you use those, that can work for the classification or regression task at hand, but looking at the data directly will not really help you a lot to understand what it really means. Good, now I address the question about what is the right classifier for my task, or regression technique for my task. And basically, as I said, it depends a little bit what you want to do and how your data is structured. We see here we have different input data. One where you directly see, this is a classification example, that you see red and blue are kind of already separated well. Here we have a very different example, because red is around the blue, so getting a straight line here is very, very hard. Here it's better to separate it with a line. And you see there are different techniques now here. Nearest neighbor classifier, linear SVM, there are nonlinear SVMs as well, Gaussian process, tree-based mechanism, random forest, and so on and so on. So sometimes it's really a little bit trial and error what works best with your data. So there is no magic recipe that always gives you the best technique or the best model. Good, then let's go to a short example, and here we use the digits in its fullest, not just loading the data set, but also transformation and classification. What we used here is first the datasets API from scikit-learn, load the data set, we reshape it. So basically it's 2D metrics and we want to linearize that. Then what we selected here is a support vector classifier. So basically using a support vector machine for classification, some hyperparameter. And now we have this is a train test split. I said we have a large data set and we want to, of course, apply that trained model to some unseen data. But if we only have that data set, we can split it into a training part and a testing part. So this is basically what this function does for you. You pass the data, you have the targets, so basically the labels of the data. And the test size is, I split it now 50-50. So we have 50% training data set, 50% testing data set, and you can also select whether you want to shuffle that. For example, if you collected the samples in a certain way, it might be that you bias the algorithm by not shuffling. But here in this case, I don't care. I set shuffle false. Then you can use this classifier and train that. So training in scikit-learn terminology is called fit. So it's a fitting that is happening inside. And you can say I use the training X data and the training labels to fit the classifier, and then I can apply that to unseen data, which is basically my test data set. So I don't know, 12 lines of code and you have a working classifier. That's actually pretty simple. So then the question is, how well does my code do? How well is my model performing? And there are also different predefined metrics available in scikit-learn, such as a classification report that contains different metrics, such as recall, precision, F1 score, and so on and so on. So you can basically get a summary how well your stuff is performing quite easily out of the box without programming much boilerplate code. You can also print that and say, okay, how many hits do I have, or what was my accuracy? So I see here a very good accuracy, but sometimes there's a misclassification, for example, here. So the real true label was 6, but it was assigned to 1. So you can directly see that visually. Good. Any questions to classification? No questions. Okay, regression. So short reminder here, classification, predict categorical attributes. Regression, we are basically focusing on continuous values. It's slightly different. And there are also different types of regression. So we have linear models like ridge regression, Bayesian models, SGD, so stochastic gradient descent models that try to go in the best possible optimization direction. We have nonlinear models, support vector regression, kernel ridge regression, nearest neighbor techniques, also decision trees. I have a short example on the right-hand side here. And ensemble methods, which are also very powerful. One is random forest. It's basically considering different trees, so a combination of different trees for the same data set. Or you split the data set and apply a tree to each of the splits. And then if you apply it to unseen data, you basically pass this unseen data to each of the trees and then do some kind of reasoning. For example, I use the average decision or majority approach or stuff like that. So here we see an example with decision tree regression. So we have different features and a certain decision in each node of the tree. So here we have, for example, the first feature, if it's under 20, we go this path, otherwise we go this path. And at the end, at the nodes, we have some kind of value that is basically trained from the fitting mechanism. So if you apply unseen data, it will go exactly the same path as here, depending on the different features, and then predict a certain value. Now this is a very shallow tree. You can imagine you can have trees that are, I don't know, 20 levels, that you have a little bit more different values. Here we have basically 5 different values that it could predict. If you have 20 levels, you have much more. Good. Ensemble methods. Random forest, I already said that. So the idea is basically you have your data set, you split up your data set in different sets, and then train a separate tree using that set. And then at the end, if you apply unseen data, you can basically do a similar path. So you basically apply that to each of those trees and then do some kind of reasoning after that. Another option is to use decision tree boosting, which is also combining different trees, but here the direction is a little bit different. I hope I do have. So here it was basically splitting up the data into different sets and then training separate models. And here the idea is basically I use the data to train a model, And of course, at a certain point, I will get errors because it's not super accurate. And the idea is basically to use another tree to reduce that error. So I use the same data for the second one, but my target values are now not the labels or the regression labels, but the error that has been produced from the previous tree. So I basically stack trees to always reduce the error of the previous tree. So this is basically the idea of boosting. Okay, good. Now let's come to a different section, which is unsupervised learning. And a very, very common approach is clustering. So basically finding structure in the data and then assign the different data sets or different data samples to different clusters that either you define or that can be defined kind of automatically. Good. And the idea is basically to retrieve those labels and metrics from the trained model that can then be used in later processing steps, I don't know, for some reasoning or for some supervised learning, for example, if you want to combine unsupervised and supervised. Here, just a screenshot from the documentation. There are different models available as well. K-means, mean shift, spectral clustering, affinity propagation, and so on and so on. I will not deep dive into each of those models, but just said there are different types that can perform this clustering. Similar, they also have a small demo with different data sets. You see the data set shape here and the different different methods or models that are applied. And you already see sometimes one or the other is better for a certain case, but it's case-to-case basis. Good. A very, very common challenge in those approaches is how do you know how many clusters are available? So if you look at the data, sometimes you already know from looking at it, but this is two-dimensional data. If you have dimensions of 200, you don't know that. So of course you can print hundreds and thousands of plots in a 2D or 3D fashion and try to figure it out by hand, but this is not a practical approach and not very scalable or transferable to other methods. So very, very common question that pops up is how do I estimate the number of clusters? And there are different techniques that can help you. One is a silhouette score, and basically that score evaluates how well the clusters are separated. So +1 is the best value, -1 the worst value, and 0 is an indicator for overlaps in the clusters. So there are also packages in scikit-learn already that can help you. So basically you have your X and Y coordinates. So this is a different data set that I used here. You can use k-means with number of clusters too, some random initialization, and you can basically determine these silhouette scores that can basically give you an idea how well these are separated. And then you can try with different numbers of clusters that you kind of know how many clusters there are. Another option is to use a different method called elbow plot. And basically that also empirically tries to determine the best value, and then you can model that, and at a certain point you see there's not real improvement anymore. So it's also using some kind of silhouette scores or distances, and here we see, okay, after 5 there's not much improvement, or 6 there's not much improvement anymore. So basically that would be the desired number of clusters or the recommended number of clusters that you can select for your algorithm. And then you can go back to the drawing board and say, okay, I want to test this model, this model, this model. What is providing the best result for me with that number of clusters? Questions? No? Everything clear? Okay. So now, again, a question. What is the best method for my task? So if you're working in a specific domain, have a specific data set, what is the best method? And this is a very tricky question because it depends on very different aspects. So how much data do you have? If you have a low amount of data, you might favor some models and don't look at other models. Is it continuous? Is it discrete? What is the ratio between number of features and number of samples? That it is also a little bit going in the direction of over and underfitting. Would reducing the dimensionality be an option? If you have high dimensional data, that makes sense. If you have low dimensional data, probably not. You can also try to use high dimensional data in your models without reducing the dimension and look whether or how good that performs. Do I have a multitask or multi-label problem or binary classification? These are all questions that pop up, and there are different guides or further hints, overviews that can help you. For example, scikit-learn has a certain recommendation. So you basically start here, and then there are certain of control questions that will guide you to the correct or to the recommended area where you can look for different model types. For example, here classification, you have support vector regression, naive bias, k-nearest neighbor, stuff like that. So there is some help out there that can help you finding the right method for yourself. So there are also some other links that are linked here in this document. Data science cheat sheet, which has a similar decision mechanism that can help you. Good. That's it for the first introduction. So in terms of time, we are a little bit faster than expected. Are there any questions left?